So what are we doing today? What are we going to be doing today? I can use reasoning to show why the answer is what it is. How are we going to do it? We're going to give a reason for each step that I put on paper. And why are we going to do it? Because it's important to document why we know what we know so that we can show that our work is valid. Today is going to be a lot of, hey, let's show our work. This is what's called a proof. So sort of really advanced showing your work. Why is it that something is true? Well, I'm going to show you why. Okay, so let's begin with reasons. All right, these are reasons that we can quote to show why things are what they are. So up here we've got these first four are what we call properties of arithmetic. These up here. Basically, if I add something to both sides, I'm using the addition property. If I subtract something from both sides, that's called the subtraction property. If I multiply to both sides, that's the multiplication property. And if I divide something to both sides, as long as that something is not 0, remember we're not allowed to divide by 0, but if I divide something to both sides, then that is what we would call the division property. All right. So when we are doing stuff with algebra, when we're doing stuff with algebraic steps to it, solving an equation, these are the properties that are going to be quoted: the addition, subtraction, multiplication, and division properties. The reflexive property, the symmetric property, and the transitive property are what we call relation properties. Or equivalence relation properties, technically. In much higher levels of math, when you are talking about how numbers work together and how different things that you sort of impose on your numbers change the way that they relate, you can talk about numbers being in a different equivalence class. I think a couple weeks ago I mentioned equivalence classes modulo n. When we were doing with the remainder, if any number that has the same remainder when you divide by 4 is in that same equivalence class, here this is a different way of looking at how things end up being the same. We say that something follows the reflexive property if the thing equals itself. And this equal sign is a specific type of equivalence, equals being the same. It's not always going to be equals, right? It might be something else, like is my father, right? If in that case that statement is not reflexive, right? I'm not my own father. But for equals, then we're talking about is the number the same as itself? Yeah, usually. The symmetric property basically allows you to take the equivalence relation and flip it around. So here again, we're working with the equal sign. If A equals B, then B equals A. That would mean, with the way that we understand what equals means, that would mean that A and B are the same number, right? That's not always true with other equivalence relations, right? Again, going back to is my father, if Don is my father, then I am Don's father. That's what symmetric is saying, right? And that's not true. Is my father does not follow the symmetric property, but something like is in the same room as, right? If Billy is in the same room as me, then I'm in the same room as Billy, right? That makes sense. If Jeff is my brother, then I am Jeff's brother, right? Those make sense. Here with equals, We're looking at a very specific situation, right? Same thing with the transitive property. The transitive property sort of works like what we talked about with the law of syllogism, right? P implies Q and Q implies R allows you to skip over the middleman and connect P straight to R. Here it's the same idea. If A equals B and B equals C, then A equals C, basically allowing us to say, hey, A equals B, which equals C. So now we can skip the middleman and go straight to A equals C. And again, that's for the equals equivalence, right? That's what when we're talking about equal sign, these two numbers are the same. But we can talk about that in terms of anything, right? If I'm in the same room as John and John is in the same room as Frank, then I had better be in the same room as Frank, right? If 1 is in the same equivalence class as 4 and 4 is in the same equivalence class as 7, then 1 has to be in the same equivalence class as 7. We're just saying that if these two things share a property and then this shares a property with something else, then we can say that all three of them have it, right? And then the substitution property is basically saying if I've got two things that are equal, anywhere I put one thing, I can put the other thing. You know, it's very important that we are able to plug stuff in, right? This is the substitution property is what allows us to plug things in for something else. If I know that an angle has a measure of 20 degrees, if that angle is in my equation somewhere, I can take that angle and I can replace it with the number 20. Make it easy. The distributive property, again, this is something that you should know already from algebra, but when you go through and you've got a number multiplied to a sum of two different numbers, that you can take the number on the outside, multiply it to the two numbers on the inside, like they show here, or a difference, right? And the thing I want to point out is that this goes both ways. This is a biconditional. So what I'm going to tell you is that combining like terms, like if I've got 2x plus 3x, and I want to get (5x), what I've done in order to get there is I've used the distributive property. I've just done it backwards. So whenever you're supposed to give a reason for why something was distributed or why you combined like terms, the reason is the distributive property. Even though it's two different things, remember it's going both directions, so you can use that both ways. Okay, so let's talk about this right here. I want to know what the value of x is, and I'm going to justify each step to get there. So look at what's given. That angle AOM and angle MOC form a linear pair together. So when you are being told to justify each step, this is a specific direction here, justify each step. I'm not asking you to solve an equation. Although in order to do this, you will have to solve an equation. What I'm asking you to do is for each step that you write, you have to give a reason for it. So what I'm going to do is I'm going to model this for you. Let me make a little chart here. Oftentimes, proofs will be given on a statement and reason chart, although, you know, it's totally up to you if you want to use a statement or reason chart. But I will tell you, using a statement reason chart makes your life easier. Or in the homework, sometimes they'll make you do it as a flow chart, or they'll make you do it as a paragraph or something like that. But But I'll tell you, me personally, I use the statement reason chart pretty much exclusively. And the reason I do that is because it makes the most sense to me. Laying it out like this as a chart helps make my life simpler. Now, am I saying that that's the best way? No. I'm not saying that's necessarily the best way, but I am saying that it's a way that feels easier to me. And if you like this way, you never have to do it a different way. Like when you're writing stuff down for me, you never have to do it a different way. You can always do it this way. So I'm going to basically what I'm going to do is I'm going to detail my steps. Step number 1, I always do the given statement. Every time I've got a proof, my first statement should be the given. Well, what's the given here? Angle AOM and angle MOC form a linear pair. That's statement number 1. And why? Because it's given to us. This is the thing that we are taking as gospel and trying to show what our final answer is. This is what we're being told. Hey, this is true. Now go off and make new true things. So, we're going to go through and we're going to think about what we've done up until now. Well, up until now, in order to do this problem, we'd say, all right, well, I know part plus part equals whole. And I know that this is a straight angle, so whole is 180 degrees. So the way I'm going to write this, the measure of angle AOM plus the measure of angle MOC add up to 180. And how do we know that? Because that's what a linear pair is, right? You can either say supplementary angles add up to 180, or you could say a definition of a linear pair or something like that. Either way is fine by me. Just what I want you to do is tell me why. It's because this is a linear pair and linear pairs add up to 180, right? That's a linear pair. That's what we were told. And we know that linear pairs make 180. So if you wanted to even go more granular, you could say angle AOM and angle MOC are supplementary. And how do we know what that means? Well, that means that they add up to 180 because that's what supplementary means. But we can jump straight to this. And basically what I want you to do as you're thinking is you make a statement and then you say why. And then where does that lead? Why? Where does that lead? Why? Right? So look, what's our next thing that we can say? Well, we know that these two angles add up to 180. What are these two angles? What is the measure of angle AOM? Isn't it 2x plus 30? Isn't that what it says here? So our third step can be, well, let's take these angles and let's replace them. Let's plug stuff in by substitution, right? That's what we were just talking about in this previous step, the substitution property. Anywhere you see something, you can replace it. So let's substitute. What's AOM? 2x plus 30. What's MOC? X. And together that makes 180. And now, since we're down to all this algebra, we know what to do. We're going to take it one step at a time. I have to combine my like terms, right? 2x plus x is 3x. And what did I do to go from here to here? What did I do to be able to write 3x plus 180. Well, didn't I say that when you combine like terms, that's the distributive property? Well, so now what do? I've got 3x plus 30 equals 180. What do I do next? I would subtract 30 from both sides, right? Notice I'm not writing down the subtracting 30. I did this. How did I get it? Isn't that the subtraction property because I subtracted? And then now from 3x equals 150, what do? Don't I divide both sides by 3? Well, when I divide both sides by 3, 150 divided by 3 is 50. And again, how do I justify that I did that? Well, that's the division property. Right? That's the division property because in order to get from here to here, what did I do? I divided by 3 to both sides. And then in any math class where you are asked to prove something, at the very bottom, there's a little symbol that you put. And you'll see this in any mathematical proof, especially the high level ones at the very bottom. This right here is called a dingbat. And it's a holdover from newspaper publishing. You'll see this at the bottom of a newspaper article too. It's to tell the printer that, hey, this is the end of the article. And likewise, here what I'm saying is, hey, this is the end of the proof. Any proof that you see will have some sort of little symbol like this at the bottom. And it's basically to just say, I did it. I'm done now. This is what I was trying to do. So this is just as indispensable to the proof as the whole rest of it. This is the symbol that shows that you own what has been done above. So I do expect that this is included in anything that you write down. So I will not give you full points if you do not have your little dingbat at the bottom. Does it have to be a little square box? No. Is that the most common thing that people put down? Yeah. But like if you want to have your own thing, you do that. I'll have people they'll sign their name at the bottom, or they'll put their own little symbol that they like. That's fine. But when you are doing your proof, thing number one, the given statement will always be at the top. And then you will give a reason for every step that you put. So the first reason is always given. The second reason is, how did you get from step 1 to step 2? I used what? How did I go from step 2 to step 3? I used what? How did I go from step 3 to step 4? I used what? How did I go from step 4 to step 5? I used what? How did I go from step 5 to step 6? I used what, and so on and so on and so on, until you have the final thing that you are looking to come up with. All right. This is what we're doing. This is everything. So what I want to do is I want to give you all a chance to try it on your own. Same idea, basically. Okay. So let's go over this. Let's talk about how to do this. So remember, our very first statement should always be our given information. Every time, no matter what, always and forever. Amen. So ray AB bisects angle RAN. And we know the reason for that is because we were given it. It is given. That is the thing that is given. Number 2, so what does ray AB bisecting angle RAN tell us? Well, it tells us that these two pieces, the two angles, are the same as each other. That the measure of angle RAB is the same as the measure of angle BAN. And that's what an angle bisector is, right? That's so you can always, whenever you're looking at that, well, why is it true? Well, that's what it is. You can always just say that's the definition. Definition of angle bisector. And I will tell you now, please feel free, if you're doing this, you can use symbolic words. Like here, I use the symbol for angle instead of writing out the word angle. As long as what you're saying is clear, you're okay to break it down a little bit. So now, well, if I know this is true, I can take the information here and I can just plug it in. I can substitute, right? So using the substitution, property, I'm going to plug stuff in. Angle RAB, well, that's x. Angle BAN, that's 2x minus 75. Now, again, it's totally up to you how you end up doing this, but I want to do this as quick as possible. I'm going to subtract the 2x over to the other side, leaving me with negative 1x equals negative 75. And again, why is it true that I was able to write down step 4 from step 3? Because I subtracted. And now going from step 4, I know I can divide both sides by negative 1 to write down step 5, x equals 75. And how did I do that? I divided. That's the division property. Is that what x is? Is that what they were looking for? What's the value of x? Justify each step. I found the value of x. I justified each step. I have done what I'm supposed to do. At the bottom here, I'm going to put my little symbol. Again, whatever you like your little symbol to be. I just use the filled in little square box. That is what I get. This is what it should look like, roughly speaking. Some people are going to do from here down to here slightly differently. Maybe they take an extra step or two. As long as it's documented, I'm fine with it. But basically, step 1, step 2, step 3 should all be identical to what I have, pretty much, because what else are you going to say? But then step 4, step 5, and so on, maybe you solved it in a different way. Maybe it took an extra step or two, and that's okay. All right, now, same idea, properties of congruence. So equal signs, right? Equal signs talk about actual quantities. Congruence, we're talking about the like the shape of it. If angle A is congruent to angle B, then we're talking about the angles being identical. Not necessarily the measures being the same, although it is true that the measures are all the same, but we're now talking qualitatively instead of quantitatively, right? We're talking about how things look rather than their quantities. And that's fine, but these are the same thing. It's just with a congruent symbol instead of an equal sign. just what I talked about before. So going forward, we want to know from here to here, what did I do? So from one step to the next, all I did is I subtracted both sides by 9. Yeah. So what I want to know is what's the name of the property of equality or congruence or whatever that justifies doing that. And just like you said, hey, I subtracted, so I better use the subtraction property. Right? Now look, for part B, angle O is congruent to angle W is congruent to angle L, and then my next statement is that angle O is congruent to angle L straight away. Now, if we remember, this is the transitive property. And again, I want to sort of motivate our understanding of that by thinking about train cars, right? Transitive property, right? Angle O is congruent to angle W, and we know angle W is congruent to angle L. So let's smush them all together. And then what we should be able to do is take angle O and just be able to connect straight to angle L, right? And that's what we're doing here. So this is the transitive property. Now this last one, look at what's happening. Measure of angle E, measure of angle T, and then from here to here, all I'm doing is flipping it around, right? It's going from E first and T second to T first and E second. So when we flip like this, this is the symmetric property. Because there's symmetry, right? Those of you who have taken biology, you talk about symmetry. See how it's symmetrical? The T's are in the middle, the E's are on the outside. There is a bilateral symmetry. Those of you who talk biology better than you do math. Bilateral symmetry, right? Okay. I believe these are the last couple. And again, what we're going to do is we're going to go through and we're going to show why things are what they are. So first things first, we need to write down our given statement. The measure of angle 1 equals the measure of angle 3. And take a look at what they want us to tell them. They want us to prove that the measure of angle AEC is the same as the measure of angle DEB. They want us to show that this one is the same as this one, right? And so before we even bother starting out writing this proof, let's talk about what we notice. Let's talk about what we notice. The outside two angles are the same, and the angles that we want to show are the same, the ones that I've highlighted in green up here. It's the outside angle, but the only difference is that they both share the middle one too, right? It's the left one plus the middle equals the right one plus the middle. So if we are able to do that in our statement here, in our proof, then we're going to be able to very easily show that what they want is true. Now I'm going to be really sort of extra about this because I want y'all to see what I'm talking about. But when you do this on the homework, it's going to help lead. It's going to lead you through by the nose. It's going to show you a lot of extra. It's going to show you a lot of stuff, and it's going to give you a little drop-down menu with possibilities. So pretty much all the things that you're going to do on Math Excel are idiot-proof. Okay, because you'll be able to look and just go through and say, oh, it's obviously this one because this is the only one that's even remotely coherent. Okay, so what we're going to do is we're going to set up the groundwork for our final answer. I'm going to put this down at the bottom because this is what I know that I want to prove. And I don't know why yet. I don't know how I get from the previous step to this step. But what I do know is that's going to be my final answer. So let's work our way down to it from here. So what I'm going to be able to do is I'm going to be able to let's figure out how to get angle AEC in terms of what we've got up here. Well, isn't angle AEC the same as angle 1 and angle 2? Right? Why is that? Well, part plus part equals whole, right? Isn't that what we talked about last chapter, the angle addition property? Well, let's do the same thing for our other angle, BED or DEB, right? And that's angle 2 and angle 3. What we want is we want these to be equal. We want these to be equal. But in order to do that, we have to use our original statement, right? Well, what's missing from this statement to make it these? Measure of angle 1, but we want measure of angle 1 plus measure of angle 2. Here we've got measure of angle 3, but what we want is measure of angle 2 plus measure of angle 3. So what if I just added the measure of angle 2 to both sides? What if I use the addition property of equality? And from our step number 1, I just added angle 2 to both sides. Right? Well, can't I just... Isn't that what I want? Isn't the measure of angle 1 and the measure of angle 2, isn't that angle AEC? The measure of angle 2 and the measure of angle 3, isn't that the measure of angle DEB? So I actually don't need any more space here because now I can just say with the substitution property, I can just say, this is step 5, because I can take AEC, substitute it in for angle 1 and angle 2. I can take DEB and substitute it in for angle 2 and angle 3. And that's what I do, straight from here to here because of this. Well, isn't that what I wanted to prove? Measure of angle AEC is equal to the measure of angle DEB. I did that. So am I done? Sure am. And so I'm finished. Okay, so what I've done is I've given you the reason for the first step given, right? What's given? Segment AB is congruent to segment CD. And then I've given you the second step. We don't want congruence, we want equals so that we can do exactly what we did with the last one, right? Because AC is the sum of these two. BD is the sum of these two. They share the middle, so we are literally doing the exact same thing, right? So we're going to write it out. AC is equal to AB plus BC, and the only difference there is this is segment addition instead of angle. And then same thing with step 4. BD is the same as BC plus CD. Again, it's the same thing. Now that we have these, well, I know that I can take my equals statement down up here, statement 2, and I can add the thing that's missing. They're both missing a BC, so I'm going to add BC to both sides. And why is that? Because I'm allowed to use the addition property of equality. I added the same thing to both sides. And now the only thing I have left to do is say, okay, well, I can combine these to make this using substitution. Same thing over here. And then finally, because I need to know what I'm trying to prove, right? This is not what I'm trying to prove yet. This is equal, that's congruent. So I can say segment AC is congruent to segment BD. Because if they're equal, they're congruent, right? This is just what congruent means. And I just am going to use the congruent symbol instead of writing out that whole word. But again, that's what I wanted to prove. That's what I have. And there we go.